Hey everybody, welcome to the 7.2 video. We're going to be going over exponent properties, specifically how do they apply to rational exponents. And so I'm hoping that this list of exponent properties over here on the left should not be new to you. We're going to go over it quickly, but these are the same properties we've been using. It's just that up until this point we used them with whole numbers. Just because the exponents that we're using are fractions doesn't mean anything is changing about how they work. So, for example, when we're multiplying bases, we're still adding exponents. It's just that remember when you add fractions, you need a common denominator. So if we want to add or subtract, don't forget we need a common denominator. And again, just like we had before, if we have exponent to exponent, which if you look at this, it means that they're touching, they're going to multiply. So again, we're going to go ahead and multiply, right? To multiply, it's straight across the top over straight across the bottom. We can distribute in. Negatives still make a fraction. Remember that negatives will flip a fraction. So for example, this might be something worth writing down. If you had 2/3 to the -1, you would get 3/2. So it flips a fraction. Again, we're going to subtract like we were before, and you can distribute in. The biggest thing to remember is, in most of these, you have to have the same bases. So, for example, here and here, you need to have the same base, and then these ones were the ones where we're distributing it in. So let's go ahead and take a look at some examples. All right, I believe this is the next slide. Yep, okay. So properties of exponents. We're going to decide what we're going to do with them. And so you can see here that we're multiplying bases, and when I highlight my exponents, they're not touching. This means they need to add. So 5/3 plus 1/3 straight across is 6/3, which reduces to 2. 3 to the second power, which is 9. If I look at the next example, exponent to an exponent means I'm going to multiply. So 2/3 times 1/2 would be 2/6, which is 1/3. So my answer here is 5 to the 1/3 power. The next example, example number 24, gets a little bit more complicated. And the reason why it gets more complicated is we have the same exponent, but we have different bases. So what I can do then is I could go ahead and multiply my bases, 4 times 64, and take the 1/4 power out because the same exponent is attached to both of them. So if I do 4 times 64, if you're not sure how this works, it's 256, but it's 4 times 64. So this would be 256 to the 1/4 power. And the only reason why I know what that's going to be is that 256, we already know it's 4 times 64, and we know that this would be 8 and 8, which is 4 and 2, and 4 and 2. This 2 times 2 is the same thing as a 4, so I have 1, 2, 3, 4. 4 fours make up 256, excuse me. Okay, so we're just going to go ahead and keep doing some examples. If you feel like you're doing fine on all of this, then again, by all means, you can skip ahead. So in 256, what I'm going to do is I'm going to work with this -1/2 exponent. I'm going to make it the 1/2 and then the -1 on the outside. So 36 to the 1/2 is 6. Let me erase this so that I have some more room to write. So 36 to the 1/2 is 6. So that means I have 1 over 6 to the -1. 6 to the -1 is 1/6 because we would flip the fraction of 6 over 1. So 1 multiplied by the reciprocal 6 here is 6. The next row down, same bases, different exponents. I'm going to go ahead and subtract those exponents because I'm dividing. So 1/5 minus 3/5 is -2/5. So that means I have 7 to the -2/5. And I can make that a positive exponent remember that a negative flips a fraction, so if I have 7 over 1, this would be 1 over 7 to the 2/5. In number 27, it's a little bit different, and the reason why example number 27 is a little bit different is because the bases aren't the same. So either the exponents or the bases need to match. In this example, the exponents are the what matches. Excuse me. So what we're going to do is we're going to take the exponents out. That leaves me with 70 over 14 to the 1/3 power. And when I look at the numbers that are left inside parentheses, 70 and 14 both are divisible by 7, which means I have 10 over 2 or 5. So I have 5 to the 1/3 power. Inside the next set of exponents, let's see, I haven't done black in a bit. So I'm going to go ahead and add those. Remember what I said on the previous slide, that you have to have common denominators. So if I want to do a 1/4 plus a 1/3, my common denominator here, let's try pink, is going to be 12. Ooh, that's a hard number to see. So let's see. Okay. We'll just go back to blue. So if I want to make this 12, that means I multiply it by 3 here and by 4 here, which means I get 7/12. And so if I have 2 to the 7/12 to the 6th, I'm going to multiply these because they're touching. So 6 over 12 is the same thing as 1/2. So that would be 2 to the 7/2 power. Okay, so let's take a look at example number 29. One thing I notice here is my exponents match, which means I can take out my exponent of 2 because I could square the top, square the bottom, and then I still have my exponent of negative 1/2. So this right here is going to multiply, and 2 times negative 1/2 is negative 1. So 5/8 to the negative 1 power would be 8/5. Okay, so let's go ahead and keep going. Again, you can skip ahead as much of this video as you feel like you need. When I look at examples 30 and 31, I notice that they're similar. The first thing that I notice in number 30 is that all of them have a 2/3 exponent, which means I can do 6 times 4 to the 2/3, and I'm going to do this in a couple of steps. You could do it in one step if you really wanted to, but you don't have to. So 6 times 4 is 24 to the 2/3 over 3 to the 2/3. And because my exponents match right here, I can factor them out again. 24 over 3 is 8 to the 2/3 power. Okay, and so this is the same thing as the cube root of 8 squared. So the cube root of 8 is 2, and 2 squared is 4. The answer to number 30 would be 4. Okay, 31. When I look at my numerator, I notice that I have the same bases, which means I have 125 to the 3/9, which would be 1/3 because I'm going to add. They're multiplying, so I add, so I have 1/3 over 5 to the 1/4. So the next thing I notice is that the bases of 125 and 5 are related. And so I'm always going to make it smaller. 125 is 5 times 5 times 5, which means it's 5 cubed to the 1/3 over 5 to the 1/4. So 1/3 of 3 is 1. So 5 to the 1 over 5 to the 1/4. We're going to subtract our exponents. 1 minus 1/4 is 3/4. Okay. 32. Example 32. Again, I'm going to go ahead and subtract. Make sure we pay attention to that negative. Let me change color so you can see it. We haven't done orange in a while. So I'm going to do 10/8 minus negative 3/8. Don't forget minus makes a plus. So I get 12 to the 3/8 power. Okay, so one last example on this screen. I notice I have different bases but same exponents. So that means I can take my exponent out, and I would have 3/4 to the negative 4. So 10 times 4 is 40. And then when I multiply here, the 4's cancel out and I get to the negative third. So I'm going to deal with the negative first. If this was 40 over 1, that makes it 1 over 40. And then I would want to cube it. So 4 times 4 times 4 is 64, because 4 times 4 is 16 times 4 is 64. And then I have over 1, and then I have 10 times 10 times 10 is 10, 100, 1,000. Okay, so now we have the same type of idea but in radicals. And so the first thing that I would highly recommend is that we practice going between radicals and rational exponents. If you're not sure how to do that, pause the video, get out your notes, and do that again. So if I start out with what I have here, remember if nothing's written in there, the 2 is implied. So this is 64 to the 1/2 times 64 to the 1/3. Typically, I would say add your exponents, but because these come out to nice whole numbers, I'm not going to worry about that. So 64 to the 1/2, the square root of 64 is 8. 64 to the 1/3 means what number times itself 3 times is 64. Hopefully from the previous slide you remember that that is 4, and 8 times 4 is 32. Okay, looking at number 35. So I see that I have the 4th root of 8 and the 4th root of 2. I notice that they're the same root, so that's what I'm going to go with because I don't know the 4th root of either of them. So I have 8 to the 1/4 power times 2 to the 1/4 power. And because my exponents match, I'm going to go ahead and factor those out, which means I get 16 to the 1/4 power, which is the 4th root of 16. So if we think about what number times itself 4 times gives you 16, you should get the answer of 2. Okay, if we keep moving, 5 to the 1/4 times 5 to the 1/4 means we're going to go ahead and add our exponents. 5 to the 1/4 times 5 to the 1/4 is 5 to the 2/4, and if we reduce that, we would get 5 to the 1/2, or the square root of 5. Okay, number 37. In number 37, again, I'm going to use a similar idea to what I did in the first one, except I am actually going to go ahead and add them. So I get 6 to the 1/3 times 6 to the 1/4. And the reason why this problem is different than problem 34 is I don't know what the 4th root of 6 is. So that means I need to add my exponents. So in order to add my exponents, I'm going to multiply this one by 4, this one by 3, which gives me 6 to the 7/12. And then I'm going to multiply that by 12, means I get 6 to the 7th power. And I don't know what that is, but we could figure it out if we really, really had to. And evidently is 279,936. 279,936. The reason why it's 7 is if I multiply here, the 12s would cancel out. Okay, 38. In problem 38, we're going to use a similar idea to what we've been doing. So if I look at the numerator, the square root of 7 can be rewritten as 7 to the 1/2 power. And on the bottom, the 5th root of 7 can be rewritten as 7 to the 1/5. Because I have same bases, means I can now combine my exponents, so I'm going to combine them by subtracting. 1/2 is the same thing as 5/10. 1/5 is the same thing as 2/10, and if I subtract, I get 3/10. So I get 7 to the 3/10 power. Again, at any point in time, if you feel like you need to go ahead and pause the video to review a problem or skip ahead, you're more than welcome to. Okay, so in number 39, the cube root of 4 over the cube root of 32. Again, you either have to have the same roots or you have to have the same bases. In this one, I have the same root, which means I have 4 over 32, and the cube root is the same thing as the 1/3 exponent. 4 over 32 reduces to 1 over 8, and the cube root of 8 is 2. So that means if I had 1/2 times 1/2 times 1/2, I would get 1/8. Okay, number 40. Similar to the problem that we just did, same exponents because we have the same radicals, which means I have 8 times 16 over 2, all to the 1/6 power. And so what I'm going to do is, instead of multiplying straight out, I'm going to go ahead and reduce this. So 16 over 2 is 8. 8 times 8 is 64. So I get 64 to the 1/6 power. And what number times itself 6 times? 2, 3, 4, 5, and 6. 2, 4, 8, 16, 32, 64. Okay, so let's go ahead and take a look at the next example. When you look at this example, I hope you notice that the numerator has the same roots. So that means I have 9 times 6 to the 1/3 over 2 times 2 to the 1/6. Okay, so let's think about this. 9 times 6 to the 1/3. That means I have 54 to the 1/3 over 4 to the 1/6. And when I try to reduce that, I either have to have same bases or same exponents. Honestly, I have neither. I have neither of them. So let's see what we can come up with. 54 to the 1/3. Well, 54 being 9 and 6 breaks down into 3 times 3, and then 6 would be 3 times 2. So I have, it would be 3 times the cube root of 2. Let me explain that a little bit more clearly. So what I'm noticing when I go back to the step that I was just on is that in here, there's actually another 3 hidden. And so what I'm seeing is that because 9 is 3 times 3 and 6 is 3 times 2, 3 times 3 is 9, times 3 is 27, times 2 is 54. But because I also have a group of 3, I can pull those outside of a cube root. So the cube root of 54 breaks down into 3 times the cube root of 2. And so I'm trying to think now what I could do with that. So let's see, if this is 3 times the cube root of 2, and then I have 2 to the 1/6 times 2 to the 1/6. Maybe rather than doing this step, I'm going to back up. And so the reason why I'm struggling on this example a little bit more than the others, and one of the reasons why I'm not redoing this in the video, is I want you to see that sometimes you have to try things. So if I have 2 to the 1/6 times 2 to the 1/6, I can add them. And 1/6 plus 1/6 is 2/6, or 1/3. So this would be over 2 to the 1/3. Now remember, hopefully you do remember, that 2 to the 1/3 and the cube root of 2 are actually the same thing. These cancel out, and I'd get an answer of 3. This is definitely a difficult question, and I am not expecting in any way that you would get it. Okay? So let's go ahead and keep going. If that one confused you, please just let it go. We can go over it again another day. I promise it'll be okay. The square root of 50. 50 breaks down into 25 and 2. 25 breaks down into 5 and 5. This would be 5 root 2. Or you could say 5 times 2 to the 1/2. The fifth root of 1,215. I don't know a ton of numbers that go into 1,215, but I know 5 has to because it ends in 5. So 5 goes into 12 2 times with 2 leftovers. 5 goes into 21 4 times with 1 leftover. 5 goes into 15 3 times. there I know that 3 is going to go in. 3 goes into 24 8 times, and 1. This would be 3. Let's go with 9 and 9, just because I know that's a little bit easier. 3 and 3, and 3 and 3. So because this is the fifth root, I'm looking for groups of 5. So I have 5 3s and 1 5, which means I have 3 times the fifth root of 5. If we try the similar idea in problem 54, I know that I can say that this is 18 times 15 to the 1/3 power, because rather than having the numbers inside match, in this one we have the degree of the exponents that match. So 18 can be broken down into 2 times 9, and 9 is broken down into 3 and 3. 15 breaks down to 3 and 5. This is my group size, so I need 3 to be counted a group. So we have 3 times the cube root, 2 times 5 makes 10. Again, at any point in time, feel free to move on. So if I look at the next example, the one thing that stands out to me is I have numbers out front. So 3 times 5 is 15 times, and then I have the fourth root, which can be written as 1/4 of 24 times 2. So I'm going to go ahead and break this down. 24 breaks down into 12 and 2, 12 breaks down into 6 and 2, and 6 breaks down into 3 and 2. Here's my group of 4. Here's my loner 3. So that's the same thing as 15 times 2 times the fourth root of 3, or 30 times the fourth root of 3. One last row, 1/7 times taking the cube root. I'm trying to think, sorry, I'm doing this pretty late at night. The cube root of 1/7. I know I can break this down into the cube root of 1 over the cube root of 7. The cube root of 1 is 1, so it would be 1 over the cube root of 7. That would be how I'd simplify that. Could you take it further than that? Yes, but it's not really going to get all that much simpler. Okay, so let's think. 2 over the 6th root of 81. Well, if I break down 81, that would be 3. Let's do 9 and 9 just because it's a little bit easier. 3 and 3, and 3 and 3. So I know that 1/6 can be broken down into 1/2 times 1/3. So if I look at 81 to the 1/2, I would get 9 to the 1/3, which means I have 2 over the cube root of 9. The fourth root, in the next example, example 48, 1/4 is the same thing as 1/2 times 1/2. So I'm going to take the square root of 80 over the square root of 9. That's only 1/2, which is the square root of 80. This breaks down into 40 and 2. 40 breaks down into 20 and 2. 20 breaks down into 2 and 10 breaks down into 2 and 5. So I have 2 times 2 is 4, root 5. So I have 4 times the square root of 5 over 3, and then I need to square root that. So the square root of 4 is 2, and then I need to do times 5 to the 1/4 power over 3 to the 1/2 power. And it gets pretty complicated. I'm okay if we just leave it there. We're not really going to get into too much of that. Okay. Variable expressions. These ones are the ones where you're just asked to simplify. You're not actually asked to solve for things. Okay. So because this is getting a little bit long, I'm going to go through and talk through some of the examples, and some of them I'll just pause and the answers will appear. Again, here, because I'm multiplying bases, I can add my exponents. So 1/3 plus 1/5. My common denominator between 1/3 and 1/5 is going to be 15. So I'm going to multiply this first fraction by 5, the second fraction by 3, and I would get 8 over 15. So that would be x to the 8/15. In the second example, exponent to an exponent means I multiply 3 times 1/6 is 3/6 or 1/2. So I get the square root of y, or I could do y to the 1/2. In example 58, the fifth root of 32 times x to the fifth. The fifth root of 32 times the fifth root of x to the fifth. I can break those up because they both have perfect fifth roots. So the fifth root of 32 is 2. The fifth root of x to the fifth is x. Remember in example 59, what we need to do in order to make a negative exponent positive is bring it back to the other part of a fraction. So 1 over x to the negative 5/4 is x to the positive 5/4, which is technically over 1. Okay, so this is one of those times where I've walked through quite a few of these. I did pause the video, wrote in a bunch of things, so quickly. In 60, I subtracted exponents, 3/7 minus 1/3, got common denominators of 21. I got 2 over 21. In 61, I took the fourth root, made it a fraction of 1/4. 12 to the 1/4 is 3. 1/4 of 4 is 1. In 62, what I did is I took 5/3 minus 1. 5/3 minus 3/3 is 2/3. That's where this part comes from. 1 minus -1 is 3/2, that's where that comes from. Similar to the last one in 63, if there's no exponent written in, we write in the 1. 1 plus 1/4 is 5/4. 5/4 times 4/3 is 5/3. I applied similar ideas here. You can always pause the video as long as you need to take a look at those. Again, do as many as you feel like you need to be comfortable with them. Okay, and so we still have a few more examples here. Again, I'm going to pause, write it out, and then I'll go over it. So on these last few, what we're doing is we're breaking down radicals. In 68, it's a little bit more straightforward. It's something that you're probably used to a little bit more. So in 68, what we're looking for is a square root, which means we're going to just write out the factorization of what we're talking about. In this case, 36x cubed factors to 6 times 6 times x times x times x. So a pair of 6's, a pair of x's, and I have a loner x. Remember, loners would stay inside, and the 6x would go on the outside. In the next problem, 10 breaks down into 2 times 5. X to the fourth I broke down, or x to the fifth I broke down into x to the fourth times x to the 1. The reason why I did that is if we remember that we're taking the fourth root of x to the 4, 1/4 of 4 is 1. So this comes out front. Okay, so as I look at what's going to be left inside, okay, I'd have 10x, then I have a y and a y, which makes y squared. I have a z to the fourth, which makes z squared, and then I still have a z squared left over. And so that's the general idea of what we're doing here. So again, I'm going to just pause for a little bit, write some stuff, and then we'll go over the answers quickly. Okay, so now that I've resumed, you can see that I followed a similar pattern. I multiplied the inside of the radicals together, and then I simplified. I knew I was allowed to multiply them together because they have a multiplication symbol between them, and the degree of the radical is the same in all of them. So hopefully you can kind of follow through with some of those. Do the best that you can on the WebAssign, and we will be going over it when I get back tomorrow.